Let's look more closely at the takeoff speeds. There are three takeoff speeds. The first is the takeoff decision speed, V1, introduced in the last lesson. The second is the rotation speed, VR. And the third is the takeoff safety speed, V2, also introduced in the last lesson. During this lesson, we will look at four speeds used to define restrictions on V1, VR, and V2. The most familiar of these is the stall speed, which is abbreviated to VS or VStall. Another restriction is the minimum speed for control on the ground, VMCG. Related to this is the minimum speed for control in the air, VMCA. And the final restriction is the minimum speed at which the airplane can safely lift off the ground and continue the takeoff. This is called the minimum unstick speed, VMU. To start, let's look closely at the takeoff decision speed. V1 is the scheduled speed above which the crew will elect to continue the takeoff even with an event such as an engine failure, and below which the crew will elect to reject the takeoff if there is an event early enough that they can apply the brakes by V1. It is assumed that there is a 1-second recognition and reaction time between the event and the crew's application of the brakes at V1. For an engine failure, we call this speed VEF. Therefore, if the crew rejects the takeoff at VEF and applies maximum manual braking at V1 along with speed brake extension and throttle chop, the airplane will come to a stop at the end of the runway. The other two takeoff speeds are VR and V2. The VR and V2 speeds are determined based on the airport conditions, the airplane's weight and configuration, and the restrictions discussed later in this lesson. These takeoff speeds are set to ensure that the airplane will achieve the minimum safe flying speed, V2, at 35 feet above the runway if one engine fails at VEF. The rotation speed is set relative to V2, such that given a normal rotation rate of 2 to 3 degrees per second, the airplane will achieve V2 at 35 feet above the runway. Returning to our discussion of the takeoff decision speed from the last lesson, consider the minimum field length case. Remember that the engine-out takeoff distance decreases as V1 increases. This is due to the fact that the airplane accelerates to a higher speed on full thrust before losing one engine. And remember that accelerate stop distance increases as V1 increases. This is due to the higher speed from which the airplane must be stopped and the extra runway used during the all-engine acceleration. The actual field length must be at least as long as the minimum field length, which is the point where the two distances are equal. Because the takeoff distance and the stopping distance are equal, this field length is called the balanced field length. If the actual runway available is equal to the balanced field length, the only allowable takeoff decision speed, V1, is referred to as the balanced V1. If the actual runway available is longer than the balanced fuel length, then there is a range of V1 available. Selecting a V1 other than the balanced V1 is called unbalancing. Unbalancing may be used to increase a VMCG limited takeoff weight or a brake energy limited takeoff weight. Increasing V1 can be used to increase V1 above the minimum control speed. The minimum control speed will be described in the next section. On the other hand, decreasing V1 can be used to reduce V1 below the maximum brake energy speed. This limitation is also described in an upcoming lesson. Even with a range of V1 available, there is an absolute upper and lower bound on the takeoff decision speed, V1. The upper bound on V1 is the rotation speed, because no takeoff may be rejected after rotation. The lower bound on V1 is set by the minimum speed for control on the ground, VMCG. The minimum allowable decision speed, V1MCG, is the V1 which corresponds to an engine failure at VMCG. The definition of VMCG assumes that only aerodynamic control is available. The speed is computed assuming that there is no differential braking and no credit is assumed for nose wheel steering. The crew must be able to arrest any lateral motion within 30 feet of the runway centerline in the event of an engine failure using only aerodynamic controls. The scheduled takeoff decision speed, V1, must be within the range defined by these two requirements. Now, let's look more closely at the restrictions on the rotation speed, VR. The first restriction on the rotation speed is that it must be at least 5% greater than the minimum speed for control in the air, VMCA. This is the minimum flight speed at which the crew can maintain heading with a maximum of 5 degrees bank when the critical engine suddenly becomes inoperative with the remaining engines at takeoff thrust. VR must also result in a liftoff speed that is at least 10% greater than the all-engine minimum unstick speed and 5% greater than the engine-out minimum unstick speed. The minimum unstick speed is the speed demonstrated in flight test as the lowest speed at which the airplane can lift off the ground and safely fly away. This speed is determined at the maximum angle of attack that is physically attainable by the aircraft while on the ground. The airplane accelerates at this attitude until it is able to lift off and safely fly away. Now, let's look at the restrictions on the takeoff safety speed, V2. V2 must be at least 13% greater than the 1G stall speed. The stall speed is determined during flight test by reducing the speed at a given weight until the airplane experiences a sudden reduction in the lifting power of the wing. V2 is also required to be at least 10% greater than the minimum control speed in the air. The takeoff speeds found in the QRH, FMC, and takeoff analysis are developed to meet all these requirements. The takeoff decision speed, V1, must be above the minimum control speed on the ground, and V1 cannot be greater than VR. The rotation speed, VR, must be at least 5% greater than the minimum control speed in the air and high enough to achieve the takeoff safety speed 35 feet above the runway. VR must also result in a liftoff speed that is at least 5% greater than the engine-out minimum unstick speed and 10% greater than the all-engine minimum unstick speed. And finally, the minimum takeoff safety speed, V2, must be at least 13% greater than the 1G stall speed and 10% greater than the minimum control speed in the air. This lesson covers the takeoff climb performance requirements. The takeoff flight path begins at liftoff and extends to at least 1,500 feet above the runway. There are engine-out climb capability requirements in each of 4 segments. The climb limited weight is calculated at 0 wind conditions. The first segment begins at liftoff and is completed when the gear is fully retracted. The second segment is from the gear up point until the airplane reaches the target level-off height. The third segment covers the level flight acceleration and flap retraction. The final segment begins when the flaps have been retracted and the airplane has accelerated to the engine-out final climb speed. To start, let's first define climb gradient. The climb gradient is the ratio of the increase in altitude to the horizontal distance. In this example, the increase in altitude is 240 feet and the horizontal distance covered is 10,000 feet. The climb gradient is 240 divided by 10,000, which equals 0.024. Gradient is normally expressed as a percent. To get percent, multiply the ratio by 100. The climb gradient is proportional to the thrust-to-weight ratio minus drag-to-lift ratio. At the standard V2, the engine-out climb capability equals the minimum required when the airplane is at the maximum climb limited takeoff gross weight. Let's examine the climb gradient requirements in the four segments. The first segment extends from liftoff to the gear-up point. During the first segment with a single engine failure, the thrust is maintained at the takeoff thrust setting. The gear retraction is initiated when the crew observes a positive rate of climb. From liftoff until the gear is completely retracted, the engine-out climb gradient capability must be positive for a twin-engine airplane and at least 0.5% for a four-engine airplane. The second segment begins at the gear-up point and continues to the level-off height. During the engine-out second segment, the thrust is maintained at the takeoff thrust level and the speed is held constant at V2. The engine-out climb capability at the start of the second segment must be at least 2.4% for a two-engine airplane and 3% for a four-engine airplane. For a climb gradient of 2.4% at a V2 speed of 164 knots, the airplane will have a rate of climb of 400 feet per minute. Of all of the climb requirements, the second segment engine-out climb gradient is often the most limiting. The third segment begins at the initiation of level flight acceleration. This altitude is called the level-off height. The level-off height is determined by company policy, the FAR minimum of 400 feet, takeoff thrust time limits, or obstacles. The engine-out climb gradient capability above 400 feet must be at least 1.2% for a two-engine airplane and 1.7% for a four-engine airplane. At 1.2%, the rate of climb would be 200 feet per minute at an airspeed of 164 knots. During the third segment, the flaps are retracted to the lower settings as the airplane accelerates through the flap retraction speed schedule. The absolute minimum level-off height, the FAR minimum, is 400 feet above ground level. There is a 5-minute limit on the use of maximum takeoff thrust. An AFM appendix is needed to extend the time limit to 10 minutes. If maximum takeoff thrust is needed to maintain the required gradient capability in the third segment, the 5-minute limit defines the maximum level-off height. If maximum continuous thrust is sufficient to maintain the required gradient, the second segment may be extended beyond this maximum level-off height. This extended second segment can be used to clear obstacles that lie in the third segment. The final segment is the flaps up climb segment. This segment begins when the flap retraction is complete and the airplane has accelerated to final climb speed. The thrust is set to maximum continuous thrust, MCT. The minimum engine-out climb gradient capability is 1.2% in this segment for a 2-engine airplane and 1.7% for a 4-engine airplane. The final segment and the takeoff flight path is complete when all obstacles have been cleared or the airplane has reached a minimum of 1,500 feet above the airport elevation. Any of the climb requirements may limit the maximum takeoff gross weight. If a requirement cannot be met, the takeoff weight must be reduced until the airplane climb performance meets the climb requirements. This lesson covers obstacle clearance requirements. The FAA regulations state that the airplane must clear all obstacles that lie within 200 feet horizontally while in the airport boundaries, or within 300 feet horizontally after passing the airport boundaries. The ICAO regulations require that all obstacles within an increasingly wide splay be considered. To begin, let's define the terms gross flight path and net flight path. The gross flight path represents the actual engine-out performance capability of the airplane. There is a net-to-gross difference of 0.8% for a 2-engine airplane and 1% for a 4-engine airplane. The net flight path must clear all obstacles by at least 35 feet. Let's look at the flight profile for an obstacle in the first or second segment. The net flight path clears the obstacle by 35 feet. The gross flight path gradient is greater than the net flight path gradient by the net-to-gross difference. This means that actual clearance increases with distance. If there is more than one obstacle, the critical flight path is the one associated with the most limiting obstacle. Let's consider obstacles in the third segment. Again, the net flight path must clear the obstacle by at least 35 feet. The actual gross flight path will be higher because of the net-to-gross difference during the first and second segments. The net flight path will extend further than the gross flight path because the net-to-gross difference will be expressed as an acceleration reduction during the level flight. Obstacles in the final segment have the same requirements. However, these are normally not limiting because they may be avoided by turning. The net flight path must clear the obstacle by at least 35 feet. The gross flight path gradient exceeds the net flight path gradient by the net-to-gross difference. An obstacle from any segment may be the most limiting. This lesson covers the maximum tire speed limitation and the maximum brake energy limitation. The maximum tire speed limitation restricts the maximum speed of the airplane while on the ground. The tires are certified to a maximum speed. The rating is given in miles per hour. The airplane's ground speed must not exceed the maximum rated tire speed. The airplane reaches its maximum ground speed at liftoff. If this speed exceeds the tire speed limitation, the weight can be reduced or the flap setting can be increased. In either case, the rotation speed, VR, is reduced, which leads to a lower liftoff speed. The brake energy limitation is associated with the maximum amount of energy that the brakes may absorb and still be effective. It is expressed as the maximum brake energy speed, VMBE, for a given takeoff weight. The maximum possible brake energy absorption occurs at the maximum weight and speed from which the airplane has been demonstrated to stop using maximum manual braking. This maximum brake energy occurs when the takeoff is rejected at the takeoff decision speed V1. The amount of energy increases with increasing weight and increasing V1. If the amount of energy is greater than the limitation, V1 must be reduced until it is equal to VMBE for that takeoff weight. This may be accomplished by unbalancing or reducing the takeoff gross weight. This will decrease the amount of brake energy absorption. This module describes the principles of improved climb. To start, remember the basic takeoff performance limiting conditions: fuel length, climb, obstacle, tire speed, and brake energy. When the airplane takes off at the fuel length limit weight and experiences an engine failure at VEF, it will just reach the minimum takeoff safety speed, V2, at 35 feet above the end of the runway. This V2 speed is the minimum possible speed for the takeoff gross weight. This results in the minimum required fuel length for that takeoff gross weight. Now, consider the case when the airplane's weight is climb limited. When taking off at a weight that is less than the fuel length limited weight, the airplane will reach the minimum V2 before the end of the runway. Therefore, there is extra runway available that can be used to accelerate the airplane to higher takeoff speeds. Let's look at how climb capability changes with speed. The graph shows the climb gradient capability for the standard takeoff safety speed, V2. At the climb limited takeoff weight, this gradient is equal to the minimum required gradient. In the case of a two-engine airplane, the minimum is 2.4%. For speeds greater than this speed at the climb limited takeoff weight, the climb gradient capability increases. This is due to the increased aerodynamic efficiency. The climb gradient capability is now greater than the minimum required. Therefore, this extra capability may be traded for increased weight at the minimum required climb gradient. However, at the higher weight, the overall climb gradient capability is reduced. The maximum weight increase occurs when the FAR fuel length equals the available runway. To achieve the higher V2, the rotation speed, VR must be increased. Because of the increased weight, the V1 speed must be increased to ensure that if an engine fails at the critical speed, the airplane has sufficient speed to continue the takeoff. Because these takeoff speeds are higher than the standard takeoff speeds for the improved climb weight, the takeoff speeds in the FMC and QRH are not applicable. The takeoff speeds must come from a takeoff analysis or from dispatch. With improved climb, there is an increased chance of being limited by brake energy or tire speed limitations. V1 must not exceed the maximum brake energy speed, and the liftoff speed must not exceed the tire speed limit. Another benefit of improved climb is the possibility of increasing an obstacle-limited takeoff weight. The increased climb performance may be used to increase climb gradient or takeoff gross weight. In the case of obstacle clearance with improved climb, Part of the increased performance is used to increase climb gradient, and part is used to increase takeoff gross weight. The portion of the increased climb performance that must be used to increase climb gradient depends upon the distance of the obstacle. The extra climb performance is due to the increased speed. However, to get this extra speed, the airplane does not lift off until further down the runway compared to the standard case. To start, consider an obstacle that is very distant from the end of the runway. The extra climb performance will be traded for increased weight as described in the previous improved climb section. However, because the airplane lifts off further down the runway, the obstacle is closer to the liftoff point. Therefore, the airplane will need to climb at a higher gradient to clear the obstacle. In the case of a distant obstacle, this increase in the necessary climb gradient is relatively small, and most of the improved climb capability can be used to increase the maximum takeoff gross weight. Consider an obstacle that is close to the end of the runway. In this case, the increase in the necessary climb gradient is much larger. Therefore, out of the available extra climb capability due to improved climb, most of it must be used to increase the climb gradient. Therefore, the increase in the maximum takeoff gross weight is less. If the obstacle is very close, there may not be any increase in the maximum takeoff gross weight. Each obstacle clearance problem must be analyzed individually to determine whether improved climb would be helpful. This lesson will discuss how stabilizer trim setting is chosen and where information about stabilizer trim setting can be found. Stabilizer takeoff trim setting is chosen to meet several different requirements. Stabilizer setting is chosen to produce desired column forces during the takeoff rotation. The setting is also chosen so that the airplane is very nearly trimmed for the all-engine V2 plus 15 condition and for the engine-out V2 condition. Stabilizer trim setting for takeoff is presented in your Quick Reference Handbook. Trim setting may depend on combinations of airplane weight, center of gravity, flap setting, and takeoff D-rate for different Boeing models. For example, to find takeoff stabilizer trim setting for the 737, find the correct table for your takeoff flap. Enter the table with your anticipated brake release weight and the takeoff center of gravity. Read the required stabilizer trim units. This information is the same that you will find on your takeoff reference page of the FMC if you enter the same reference conditions. Stabilizer trim settings are valid for assumed temperature reduced thrust and for improved climb takeoff, but may vary with takeoff D rates.